short gamma ray bursts, yes, you don't only expect a jet, you expect many materials accelerated at middle relativistic velocities. For example, the short breakout material, the ejectant material, yes, and others. But in the case of long gamma ray bursts, you expected only the jet and not the middle relativistic ejectors, for example.
Well, yeah, you have the cocoon of the gamma ray burst. As the gamma ray burst, as the relativistic jets interact with the star, it creates also cocoon. So
you have cocoon, you have
that's relativistic.
That will move at mild relativistic velocities at the beginning, and later it will decelerate as it moves away from the.
And you also have a wind. The Wolf-Rayet had a wind. So you also
but that's not mildly relativistic, no? That's 10 to 8 centimeters per second, no? The velocity of a Wolf-Rayet.
Mm-hmm. But you have jet cocoon in both cases.
Mm-hmm. In both cases. You have jet cocoon in both cases.
But the question was, and I think it's very interesting, no? And I don't have any idea about the answer, so it would be great if someone knows about it. So the magnetars and the collapsar produce the same jet or not?
I think one of the big questions, for example, in a short GRB, is how long will the magnetar, if you form one, how long will it survive? Because if I understand correctly what Nissim was saying, you are using the slow down velocity of the magnetar to power the jet. So the magnetar is slowing down. If the magnetar slows down, it's a very, very massive object, probably 2.5 to 3 solar masses, and that will eventually collapse to a black hole. So how long do you have the magnetar for? And can you explain everything with that amount of time? Of course, if you form a black hole, it will not be a very rapidly spinning black hole, maybe 0.3 for the Kerr parameter. So could you still power something through something like Blanford-Snayak or something like that? So could you have both engines working for a short GRB? In the case of a collapsar, it could be different. And I guess it will depend on how massive the core that collapses actually. But in the case of a short GRB, the mass is very, very large, most likely. But it's of course, it's still an open question. What's the limit between the maximum neutron star and the black hole, right? But in most scenarios, it seems that 2.1, 2.2 solar masses would be very close to the maximum mass of a neutron star. So a merger of 2 neutron stars will likely collapse rather quickly. So the thing that will hold this engine on for a little while is centrifugal force, but that's the one you're using to power the jet. So it most likely won't survive too long. So if it survives 1 or 2 seconds, maybe you are through. But it's not clear that you can survive for that long. Anyone else?
Hi, Veronique has had to leave, so I'm supposed to be leading this discussion, but I have nothing to say because it's all theory stuff. But go on, you theorists, have at it.
Well,
so William, what do you think? Do you know?
I will see if he is around.
I'm sorry, I had to disconnect for a bit, so I missed the beginning of this discussion.
Yeah, so the question by Jean-Luc was, if you have a magnetar or if you have a collapsar, will the jets be different in the 2 cases or not? The structure of the jet will be different?
If you have a black hole or a neutron star?
Substantially, yeah.
Well, yes, in the sense that the magnetar is more likely to give you more baryon pollution at the core. And so you might probably want to wait until something collapses before a useful jet is launched. So that may induce a delay. And there's an additional source of neutrinos if you have a magnetar, because it's hot at the center. So
and what about
What?
Variability won't be able to distinguish between.
Well, I mean, rotation would maybe imprint some variability, but I'm not sure it would be. It would be filtered through many other things before you can actually look at something observable.
But it's not. I'm not sure if it's clear that the variability you observe in GRBs comes from the central engine. I don't think that's the case.
Oh, I'm sure
Maybe
it's not clear.
Right. Right, but I mean, you cannot see the central engine.
That's right.
So the variability is not necessarily coming from there, but probably from internal shocks much further out, right? So unless you could observe variability in neutrinos or something that's really coming from the inside, it's hard to tell if I mean, yes, you could have lots of variability in there, but it's not clear that you will be able to get it in your signal.
Well, there are different layers of variability, right? You can have variability from an accretion disk, from the rotating engine, from the jet production, and from the internal shocks. So if you really want to build different layers of variability, you can do that, but you should consider them all and then maybe do a power spectrum on some of them. At some point, some of you may remember Augusto Carballido. We did a few simulations of neutrino cooling in disks because the process that produces the cooling has very sensitive dependence on temperature. The powers are very high. And so the variability of the dominating cooling process imprints a signal on the variability in the disk. And if that in any way gets translated to the power of the jet, then you may see something outside. But you need to do power spectra of the variability and see what sort of power law and what sort of features you get in that spectrum. And there's a number of studies that have done this for observed GRBs in the prompt emission over the past few years. But this is what I mean, you have to do the layers. I mean, if you think it's a disk and you have to start with the disk and then add the central object and then add the jet, and every layer will add its own signal, and at the end you get a convolution of all of these. But there are so many variables that it's complicated to isolate any one of them. The collapse of a central object to a black hole or the remaining of a central solid object, I think would probably have a direct bearing on the lifetime of the jet. And that's maybe something that is more direct.
So William, you remember, I don't know if you remember, and Alan, that we had several meetings, tried to say if the GRB18, I remember the name that Rosa worked last year, if was a short or long gamma burst with Eleonora and many tests. We did several tests and we didn't. Remember, Rosa?
18,
we didn't.
04, 18.
Exactly. We didn't. We have the variability, we have the duration, we have the afterglow, exactly, the hardness ratio, but we didn't.
We need more data.
Well, I think we need more data. I think we need a better theoretical understanding.
That's the easy answer. Thank you.
I mean,
I
don't
discuss with theoretician. It's not possible.
Can I ask a question to Enrique on something he just said?
Okay.
You say that in the case of a magnetar collapsing to a black hole, you get a spin of 0.3.
Well, I'm not saying, what I'm saying
At
is
most 0.3.
A neutron star spinning at breakup velocity, so basically as fast as it can before it starts shedding material, does not have as much angular momentum compared to what black holes can achieve. So yes, a very rapidly spinning neutron star will, if it collapses to a neutron star, to a black hole, sorry, will not be much more than 0.1, 0.2. Maybe in some extreme cases, if it has not lost energy to launching jets or something like that, it could get to 0.3, but not much more than that.
And if the interacting neutron star collapses directly to a black hole, in that case, the spin is larger or not?
No, usually it depends also on the stellar evolution previous to that. But most of the angular momentum, if you get it, will come from further out. So layers which are further out have a larger lever arm, so have much more angular momentum, and that's where you would expect to have very large Kerr parameters for your black holes. So usually a neutron star won't be able to do that, and even if it had enough angular momentum prior collapse, it will not be able to fall in until part of that angular momentum has been dissipated somehow. Otherwise, it tries to collapse and there's too much centrifugal force and you start shedding material.
Okay, thanks. Because in the extragalactic community, people doing TDEs, jets from TDEs, they say that you need a very large spin, no, to produce a relativistic jet. So Narayan, Chekovskoy, and so on. So that's an interesting point, no? Thank you.
There's several open questions there, I think. The angular momentum is one of them. How long the object survives is another one. So I think you would need differential rotation to keep it living long enough, especially for long GRBs. And if it acquires enough mass and enough angular momentum, it will collapse. Then I guess your central engine will be a black hole.
There is a question from Diego. Potential.
Yeah, but it's different from this. So if you want to finish this.
There's, so regarding magnetic fields also, I think Nissim, you were mentioning 10 to the 17, which is, wow, it's, it's very, very large, 10 to the 17 Gauss. You are just an order of magnitude of, from producing proton antiprotons, just from the magnetic field. So
I think something will break before you get to 10 to the 17.
Exactly. I don't know if the star itself will will get all messed up just because of the magnetic field. Yes. And on top of that, if you need 10 to the 17, that's outside the magnetar to power your model. Inside, it is likely to be much larger. So you could have these 10 to the 18, and yes, like William says, things start to break up before that.
Okay, so I'll ask my different question then. And so this is for the observers, more like I guess you've seen that us theorists and numerical simulators, we're quite intrigued and very fond of now the off-axis jets. So if we can see them by off-axis, and then my question is to start, if Colibri had been already in 17th of August 2017, would Colibri have seen any counterpart of this GRB, short GRB?
Of 170817.
Yes.
Yeah, it was 170817 was like 17th magnitude.
Okay.
So that's even bright for spectroscopy.
How far could we push 170817 to still Colibri be able to see it? Do we know? Like 100 megaparsecs?
Easily a factor of 10 in distance, probably a little bit more, factor of 20 or 30. So, you're getting out to good fraction of your parsec.
Yeah, nearer than to the 200 megaparsec, it would be possible.
And so, are we way better than other optical telescopes, like SWOPE and all those that did see? Or are we comparable? Or how is Colibri, say?
We have In terms of basic sensitivity, we are comparable to many other telescopes. I think we have two advantages. One is that there aren't many telescopes, but they do exist that have a larger field of view. You know, they tend to be the big specialized things like DECAM and Palomar, but compared to normal observatory telescopes, we have a much bigger field of view. They're typically 5 or 10 arc minutes, and we have 25 arc minutes. The other thing that we have is we have simultaneously we get 3 colors, and that is scientifically useful, and it's also effectively creates, instead of having one 1.3 meter telescope, we have 3 observing at the same place, and that's a big help. But no, we're not going to be orders of magnitude more sensitive than our competitors.
No, but we are going to be comparable with the competitors, and as you say, there's these many more filters.
If you want to have another reference, we have what we call visible telescope on board the swarm. And Colibri is more sensitive, slightly more sensitive than the VT. And we have, as explained by Alan, we have 3 channels with standard filters that we don't have on board. So it's very interesting. The advantage of the VT, to be honest, is that as it operates in low orbit, the probability to detect a gamma, to be able to observe a gamma burst is larger, because typically we are 50% more efficient than Colibri this way, because we have the day-night effect on ground.
And so say a neutron-star merger happens. How many seconds will pass? Like from the MOU and then Colibri, like where is the, how do you call it, the bottleneck?
But it depends. If we can observe immediately, if it is, okay, it's not too low, it is a night, we don't have the moon, close to the object.
Yeah.
It was computed. We can be on the target in 1 minute. 1 minute is from the trigger on board. It typically takes 30 seconds from the alert coming from the board to the telescope. And then you have 30 seconds to stop the ongoing observation and start the new observation.
But it depends on the trigger. Yeah, okay, I mean, so if we detect a gamma ray burst either with SWARM or with SWIFT, we can get there in seconds. But if it's a Fermi detection, or if it's a LIGO, Virgo, Cagra detection, we have to localize first, and that is a long and difficult process.
But we have an advantage. We have different telescopes at the observatory.
Yeah,
it's clearly an advantage that we have.
And do you also get signals from LIGO? I mean, even if SWARM or Fermi take their time, LIGO could also help, right?
Yes, this is the
The
idea.
problem is that the LIGO error box is so large, and it will be larger for most of the case. We have seen in O3.
Yeah.
We have seen 10 neutron star, or nearly 8 or 10 neutron star merger, and we never localize it.
But yes, for 3, but for 4 or 5, it's different.
And that's where we lose all our time. And you cannot imagine the number of telescope and time that have been followed.
I agree with Damien, actually. You can hear me?
Damien?
On entend même que toi, Damien. Tu as beaucoup de bruit là.
C'est vrai?
Ouais. Afficher un peu ton micro.
Yes, if I can.
Is it better?
Now it's nice.
Now it's okay?
No, you are far away now.
Low.
Now faint.
and now?
Perfect.
Okay. So yes, I agree with Damien. On this point, if you talk about sensitivity, yes, Colibri is great. If you think that you are going to localize the neutron star merger very well, I think short GRBs detected by them will be mainly at cosmological distance, so it will be probably very far away. And the closest neutron star merger that you are going to detect will be detected probably by LIGO and Virgo. And in this case, or you can expect maybe Cagra, but in this case, you will have a pretty large localization. So with the field of view of Colibri, you will have to wait, I think. It will be hard, I think, with such a field of view, but we can try we can expect from 04 that the LIGO Virgo localization will be much better, but I mean, yes, I agree. It's not clear at all. I mean, 03 has shown this.
Larger.
Well,
Because the horizon distance for the different detectors are not the same to detect binary neutron star mergers. So Virgo, it was something like 120 megaparsec, and LIGO's was about 200 megaparsec. So if you have something at 200 megaparsec, you cannot detect it with Virgo. So
can I maybe add something? It's true that it's very difficult to make some predictions on how large or how small will be the error maps from LIGO Virgo. However, if you look at 03, during which there was only one confirmed BNS event, when I mean confirmed, I mean that the probability that it being a BNS was larger than, say, 80%. There was only one, which was 190425Z, if I'm not mistaken. And in that case, the error box was very large, and therefore it's very difficult for small field of view telescopes to be able to cover all of that area within a couple of nights. However, for other facilities, for example, the ZTF, the Zwicky Transient Facility, which is in California, they have a field of view of, I think, 47 square degrees or something, which is huge, and they were able to cover all of the sky map, which was accessible to them, because they can't observe all the sky, of course, because they're in the northern hemisphere, etc. But they were not limited by the localization area, but only by the position in the sky of the sources. They were able to cover everything with a declination larger than minus 31 degrees or something. So maybe in the future with such events, you could expect these very large field of view telescopes to cover all that's possible to them, if they're lucky to detect the transient. Then afterwards you have to identify it, which is very difficult. Even with spectroscopic data, it's difficult to tell a kilonova from a late supernova or something, or even from color evolution. It's very difficult to tell a kilonova. But then afterwards, if you're identified, I think that's when the smaller field of view telescopes will be interesting, because that's when we'll be able to have a very, very well sampled light curve in all of the bands for the event. So maybe that's where the smaller field of view telescopes will make the difference when you observe a kilonova.
Oh, sorry. So
can I make a comment on that? So yeah. I'm more pessimistic.
Yeah.
In that, for the events where you have very large areas, I mean, there's a bunch of us who've done telescopes, and we're aiming to get observations over dozens or maybe a couple hundred square degrees. But if you give us 1,000 square degrees, sometimes we can cover it. But the problem is we turn up so many false positives that it makes it impossible to decide which is the real event.
Right.
This is made worse by the fact that the low signal to noise discoveries tend to be further away. So you're looking for fainter objects. It's really difficult, even if you get the observations, to decide on these low signal to noise events, what are the useful transients. I agree with Damien's comment that one of the advantages, I think it's better that we're going to get, say, 1 in 10 events which are a factor of 2 closer, and those are the events where I think we might have a better chance of localizing them where they'll be brighter and where we might be able to have a reasonable number of false positives.
Right. Yeah, I absolutely agree, because the localization area for a 3 detector event, or let's say a localization area for a whole network event, goes as the square of the pseudo-to noise ratio. And so if we're counting on closer events, then indeed we'll be able to localize them. But then, as you just said, Alan, what's very difficult is to identify kilonova, either from color revolution or from spectroscopy. That's very difficult. And also, of course, the magnitude problem, because if you take a 17817, that's magnitude 17. If you put it out to the horizon for 04, which is something like 300 megaparsecs, then your magnitude 21, 21 and a half. And, you know, that is a reach.
But that's event we will never, if it's at the horizon of LIGO, we will never observe that, because only LIGO will be, because Virgo, it will be 100 megaparsec, and if Cagra will arrive with a quite reduced horizon. So to get a 4-fold coincidence, it means that the event will be close. Otherwise, we will never get the.
Okay.
Yes,
that's the problem of 03. To get 3-fold coincidence, we get very, very few events at the end on BNS. We have BNS candidate, but they were only with the 2 LIGO or with 2 LIGO plus little Virgo, and that's what was really difficult for the detection. That's true that there is only one confirmed, but there were other candidates, and that's the difficulties is to, we can observe something at 200 megaparsec, okay, but after the error box will be very, very large. And cover them with only small telescope will be hard.
Yeah.
If you don't get any space, any space counterpart, because they can cover Eclair, for example, or BAT can cover very large field of view. But if we want to do it with the MXT, with the XRT, it's really a pain.
Well, with luck, we could have a short GRB detected by SVOM in 100 megaparsec, maybe.
Yeah, of course.
It's a lot of luck.
Let's hope. But that's true. That's true that we don't know what will be the horizon distance for BNS detection for Virgo in 04 and for Cagra also. So let's hope that maybe we will have a 150 megaparsec horizon distance for the 4 detectors, but I don't know.
Right.
For Virgo, maybe we will.
But on a more optimistic point, in French we say "qui peut le plus peut le moins," which means that basically, if we detected 170817 back in 02, the detectors improved so they can see further, but they can also see the ones that we could already see. So I mean, we can still hope for events.
See how lucky the Virgo LIGO were to detect this event.
Yes. I'm sorry, what?
You see how lucky all the community were to detect this event, because this event is a really golden or whatever, a platinum, or I don't know what is event ever.
Yeah.
Population
studies show that events like 17817 were extremely, extremely rare. Yeah.
But at least we will try, and we have a plan to follow gravitational wave with Colibri. Not exactly how, let's see what will be the performance of LIGO, but we will try to do it, or at least to do some characterization if we cannot.
And at least we have a telescope that is able to make color evolution studies.
Exactly.
But so it's at least something. We did our job, and we are waiting for the gravitational wave guys to do their job. I'm just joking.
No, it's a nice conclusion for today.
They're observing. We're not observing yet. So I'm not sure I'd say we did our job yet.
Yes, that's right. That's right.
Are there any other questions on this or other topics?
Yeah, when is the one with neutrinos coming along?
Damien, it's for you, this question.
Enrique is volunteering to take charge of this.
No, but it seems that if you look at the TXS event, it seems that Master has found some very, very significant evolution time variation in their Lie curve, and seems to be quite constraining in this P gamma model. So I was thinking that it was difficult to detect some optical variation and to relate them to the very high energy gamma rays or neutrinos, but it seems that there is a relation. So it's, and for example, 1708 was at magnitude, no, TXS was at magnitude 15, the blazar. But at one point, it's important also to look at this, for example, for the blazar.
But you can't expect gravitational waves from a blazar, right?
And if we have a gravitational wave neutrino and all the electromagnetic spectrum together, but I think you can go in retirement after this event.
Or as you say, you must be very, very, very lucky.
Yeah.
But as you put it, you just need one event.
Why not? No, nobody knows.
I think that the best bet for an event which is in all three messengers is a galactic supernova, of course.
Yeah, of course. But this we need to be lucky also.
Yes, I think we need the R136 to get going with all these massive stars being produced there. Probably that's our best hope.
And speaking of bet, we need to make a bet on whose birthday the next Goldie Lock neutron star will fall, because there's two of us here that were born on the 17th of August. So we
Who's the other one?
Maggie.
Maggie's birthday is also okay.
Yeah.
Right.
So two of us were born on the 17th of August. So we need to see who's next going to be the lucky one.
Bueno, muy bien.
Okay, do we have other questions or anybody else want a comment perhaps? If not, then I'll say goodbye to everybody. Thank you, our speakers, once again.
Maybe,
see you guys tomorrow.
Wait 1 second,
tomorrow morning.
Alan. I have a question because I don't know if Bruce Jean will be here tomorrow. He said he had a problem. If in case, so I will ask him the question, in case he could not come, would you be ready to start, Rosa? Tomorrow?
If you don't come tomorrow.
No, if Bruce Jean doesn't come.
Don't worry. We start at the same hour, please. Yes.
Okay, we start at the same hour. I don't know. Maybe
yes,
he didn't say. He didn't give any extra news, so I suppose he will come. But in case he's not here, do you agree that we start with you?
Yes.
And I give you 30 minutes for that.
Okay. Perfect. Well, look forward to that.
Tomorrow is the day for observation.
Okay.
Okay.
All right.
Tomorrow.
Thank you all.
Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye.
Nice.
Bye-bye.
Thank you very much.